Namaskar. So, in last class we discussed about source free RC circuit response. In this class we will discuss about the RL circuit, and we will particularly see when the source is not available how the circuit will respond. So, now let us start the second lecture of this week. We will discuss about the source free RL circuit. Now, if you see the RL circuit which we will consider for today's discussion is RL circuit, you can say that L is connected in parallel, or you can say that the elements are connected in series in a loop. So, now the goal of the particular circuit analysis is that we will try to find out the current that is IT, which would be flowing through the inductor. Now, we have selected inductor current as a response because we know that the current through inductor cannot change instantaneously. So, similar to your RC circuit where capacitor is capacitor voltage cannot change abruptly, similarly here the inductor current cannot change instantaneously. Now, let us assume that at time t is equal to 0, the inductor has an initial current I naught, and we can represent I at time t is equal to 0 is nothing but I naught. So, let us analyze the circuit. The energy which would be stored in the inductor initially. So, we assume that there is an initially energy stored in the inductor, and we represent it by W at time t is equal to 0 is nothing but half L I naught square. Now, if you apply KVL around this particular loop, you will see we have considered the polarity for inductor as plus at the bottom and minus at the top, and in that case the sum of the total voltages, if you consider in a loop, would be 0. That means, VL is equal to VL plus VR equal to 0. Now, we know that the value VL, that is voltage across inductor, can be given by the value called L di by dt, and VR is nothing but I, that is the current flowing in the loop. We have shown that current as I. So, the VR, that is voltage across resistance, would be I into R. So, we can simply write L di by dt plus R into I equal to 0, or you can write as di by dt plus R by L. If you take L in the denominator here, R by L into I is equal to 0. Now, when you see this equation, you can use the integration technique to solve it, as we did in the case of RC circuit. So, what we can do here, if you see simply, you can rearrange this equation as di divided by I is equal to minus of R by L into dt, or what you can do, you can now integrate both sides, then this will become I is equal to minus R by L into t, that is ln I is equal to minus R by L t plus some constant. So, let us assume that constant is ln A. This is what we assumed when we were analyzing the RC circuit. So, what we can write? We can write ln I by A is equal to minus R by L into T. So, now what we know that the initial value that we assume I at time t is equal to 0 is I naught. So, the value of A, which you will see here, is nothing but the initial value of current I. So, we can replace A with I naught. So, this will become now ln I divided by I naught is equal to minus R by L T. Now, what next we have to do? We have to take the powers of E at both sides, and we get I current, that is anyway the function of t is I naught into e to the power minus R t by L. So, if you compare it with the RC circuit where we calculated V c is equal to V naught into e to the power minus t by R c, here the current I in terms of time t was I naught into e to the power minus R t by L. So, how it will what would be the response of this function, that is I naught e to the power minus R t by L? The function would be exponentially decaying. So, it will start with the initial value, that is I naught, and then it will decay with the function E naught to the power e to the power minus R t by L. So, if you see particularly this figure, you will see that at time t is equal to tau, this will become 36.8% of its initial value. Now, what is tau? If you correlate with the RC circuit, tau was the time constant. Here also the tau is nothing but the time constant, but the value of tau would be, if you compare this with the I naught e to the power minus t by tau, then you can simply say tau is nothing but L by R, right. So, we got tau, that is our time constant for RL circuit is nothing but L by R. So, instead of writing in terms of L and R, the current I cannot be written, can be written as I naught e to the power minus t by tau. Now, what would be the voltage across the resistor? Voltage across the resistor would be, that is V R equal to I into R. I we have just calculated, that is I naught e to the power minus t by tau multiplied by resistance R. Now, instantaneous power dissipated by the resistor will be P. P is nothing but I into V R. So, if you put the value of I and V, which we saw in the previous these two equations, you can put the value, that is I naught square into R e to the power minus 2 t by tau. Now, what we want to find out, what would be the total energy dissipated by the resistor during a particular time t. What we can do? We can find out the value of energy as the integration of instantaneous power P over dt between 0 to t. So, what we get? We get the value as 1 by 2 L I naught square into 1 minus e to the power minus 2 t by tau. Now, if you see this equation, when t tends to infinity, the value of W R would be equal to 1 by 2 L I naught square. and this is what we assume that the initial value is stored in the inductor. So, that means that whatever the initial energy was stored in the inductor is eventually dissipated in the resistor. Now, let us see some important facts about the time constant. Smaller the time constant of the circuit, faster would be rate of decay of the response. So, this is similar to what we saw in case of RC circuit. So, similar to that in RL circuit also, the small time constant means faster the rate of decay of response. Larger the time constant, slower would be the rate of decay of response. Now, at any rate, the response decays to less than 1% of its initial value after 5 time constants. So, the same we saw in case of RC circuit also, when the time is 5 tau, that is 5 times of the time constant, the value of voltage was left with less than 1%. So, here in case of RL circuit, the response will decay, that means the value of current that is flowing through the inductor will reach to less than 1% of its original value after 5 time constants. Now, while working with the source free RL circuit, we have to keep 3 things in mind and we have to solve the circuit accordingly. First is that we have to find the initial current which is flowing through the inductor, that is I 0, I at time t is equal to 0, let us say it is I naught. So, this is something which we have to first identify from the circuit, then find the time constant tau of the circuit, and then third, the important thing is that when the circuit has a single inductor and there are several resistors connected or there may be some dependent sources also, the Thevenin equivalent would be a good option to analyze the circuit. So, we will use Thevenin equivalent at the terminals of the inductor to form a simple RL circuit, or we can use the Thevenin's theorem when several inductors can be combined to form a single equivalent inductor. So, in summary, we can say that if we have circuit where we have multiple inductors and resistors, we can utilize the Thevenin's theorem to simplify the circuit and find out the response of the circuit. Now, let us take one example so that we can clear the concept. Let us say we have one circuit as shown in the figure. Here one inductor of 0.5 Henry is carrying some current I, and in parallel with we have a 2 ohm resistance where the current Ix is flowing, and then we have 4 ohm in series with the parallel combination of inductor and resistor, and which is connected in series with one dependent voltage source whose current component, that is if the voltage source value given in the circuit is 3I, the current component is depending upon the current flowing through the inductor. Now, initial value which is given here is I at time t is equal to 0 is 10 ampere. We need to find out the value of I at time t through the inductor and find out the value of current I which is flowing through the 2 ohm resistor. Now, here we have two ways to solve this problem. One way is that we can obtain the equivalent resistance of the inductor terminal, or other way is that we start from scratch using Kirchhoff's voltage law. So, when we have to find out the equivalent resistance, we can utilize our knowledge of Thevenin's theorem and simplify the circuit to find out the equivalent resistance. Second, when we have the dependent voltage source, we can also use the simply Kirchhoff's voltage law and simplify the circuit as we used to do in case of mesh analysis. So, whatever the approach we will take, the value will remain same, but it is always better to obtain first the inductor current. Now, in first method, the equivalent resistance is the same as Thevenin resistance at the inductor terminals. Now, since we have a dependent voltage source available in the circuit, what we can do? We can use one voltage source that we let us say that the value of that voltage source is 1 volt at the inductor terminal AB, which is shown in the next slide. So, what we have done? We have removed the inductor from terminal AB and we added one voltage source equal to 1 volt. Now, we have two meshes in the circuit. Let us say the current I1 and I2 is flowing in this direction, both are in the same direction. So, let us try to write the KVL equation for both of the meshes. In this case, you can write 2 I1 minus I2, because I1 I2 will be in different direction here. So, this would be the I1 and this would be the direction of I2. So, this will become 2 times of I1 minus I2 plus 1, that is voltage source which we have connected. Since we are going from plus to minus, then it will be plus sign here. So, if you simplify, this will become I1 minus I2 is equal to minus 1 by 2. Now, for second loop, what we can write? We can simply write 4 plus 2 6. So, that is 6 I2 minus 2 I1 minus 3 of I1 equal to 0. So, it is going from minus to plus, that is why it is minus of 3. The value of this is nothing but the current which is flowing through the inductor. So, this has become now I1, because the current which is now, if we connect the inductor here, the current which would be flowing in the inductor would be I1. So, here the value of dependent current source would be 3 I1. So, this we have got now. When we solve, I2 will be 5 by 6 I1. Now, we have two equations A and B. In terms of I1 I2, if we solve, we get value of I1 as minus 3 ampere. Now, I1 is opposite to the direction of I0, which is the value of current flowing through the 1 volt voltage source. So, the value of I0 will be minus of I1. So, we get I0 is nothing but 3 ampere. Now, the R equivalent is nothing but the Thevenin resistance and its value is V0 upon I0. V0 value is 1 volt and I1 we have just calculated as 3 ampere. We get 1 by 3 ohm as a Thevenin resistance. Now, what would be the value of time constant? Time constant value will be L upon R equivalent. Value of L is given as 0.5 Henry. So, that was given in the question. So, we will put that value, and the R equivalent we have just now calculated as 1 by 3 ohm. So, value of tau will be 3 by 2 second. This value we will put in the original equation for IT, that was I0 into e to the power minus t by tau. So, this will become IT is nothing but I0. I0 is the value of current I at time t is equal to 0. So, this is given in the question. So, value of that is 10. So, 10 is there, and we put the value of tau in the equation, we get the current flowing through the inductor at any time t is nothing but 10 into e to the power minus 2 t by 3 ampere. Now, if you the second method, we apply KVL to the circuit. So, if you apply KVL, you simply put the inductor back to the circuit, then the circuit will again have two meshes. Let us take the value of those mesh currents as I1, I2, and we write the KVL for both of the loops. So, for this one what we can write, L di by dt. So, this will become half di1 by dt plus 2 times of I1 minus I2 equal to 0. So, if you simplify, this will become di1 by dt plus 4 I1 minus I2 is equal to 0. Now, for second loop, we can write 6 I2 minus 2 I1 minus 3 I1 is equal to 0. Now, since the current flowing through inductor is I1, so here the value of the dependent voltage source will be 3 I1. So, that is why we get the mesh or loop equation for second loop is 6 I2 minus 2 I1 minus 3 I1 is equal to 0. So, what we get here, I2 is equal to 5 by 6 I1. Now, let us substitute the value of I2 in the equation which we just now calculated when we were using the mesh equation for loop 1. So, if you put the value, this will become di1 by dt plus 2 by 3 I1 is equal to 0. Now, you can rearrange it them, this will become di1 by I1 is equal to minus 2 by 3 dt, or you can take the integration at both sides. You will get ln of IT by I naught is equal to minus 2 by 3 t. I naught is nothing but 10, we know. So, if you take the power of E at both sides, IT will become now 10 into e to the power minus 2 t by 3. So, this equation is again the same as we saw in the case of method 1. So, either you use the Kirchhoff voltage law directly to the circuit, or you will use Thevenin theorem, you will get the same result. So, now we have got the value of IT. Next task is we need to find the value of V, which is nothing but the voltage across the inductor. So, voltage across the inductor is L di by dt. We can put the value of inductor L and then the initial value of current I naught, because di by dt is when you differentiate IT, you will get the value of di by dt. So, this will become 0.5 into the value of I naught into the minus 2 by 3 term which is coming from here into e to the power minus 2 t by 3. So, you will get value of voltage V is nothing but minus 10 by 3 into e to the power minus 2 t by 3 volts. Now, since the inductor and the 2 ohm resistors are in parallel, that means whatever is the voltage coming across the inductor will be the same voltage which is coming across the 2 ohm resistor. So, we can calculate the value of current Ix which is flowing through the 2 ohm resistor is nothing but V by 2. So, we get finally the value of Ix is nothing but minus 1.667 e to the power minus 2 t by 3 ampere. So, with this you can use either Thevenin equivalent or the mesh analysis method using Kirchhoff voltage law, and you will get eventually the same answer. So, we close our RL circuit session today from this point. In the next lecture, we will discuss about the various sources, especially those sources which are required for the analysis of the circuit. So, if you see the particular electrical circuit, we apply either voltage or current source. So, when you apply voltage or current source, those are suddenly applied to the circuit. So, you will get one step response of the source. So, that is one important type of source which we will study. Plus, when we have the surges coming in the electrical circuit, we get another type of pulse in the circuit, that is called the pulse response. So, that also we will see how we will interpret that particular event with the help of mathematical function, because these two are required for analysis of our electrical circuit. So, we will see how we will represent both of them in a mathematical term, and then we will apply both of them into the various RC and RL circuits and see how they will behave when we will apply either step or impulse type of sources into the circuit. Thank you.